Hey everybody, Dr. A here, and in this video we're going to be providing some background information on differential leveling. But before we do that, I want to provide a little bit of background information and definitions on land surveying for those of us who maybe aren't really experienced with this. So what is land surveying? Well, another word for land surveying that you may hear sometimes is called geomatics. And basically, geomatics means measurement of the earth or measurement on the earth. And what it is it's the science, art, and technology all involved with determining positions on, above, or beneath the Earth's surface. So in engineering, and specifically civil engineering, we work very closely with land surveyors. Now, as civil engineers, we need to be familiar with a lot of land surveying practices, but land surveying is its own profession, and these land surveyors that are professionals work with civil engineers during construction and the design phases of different types of infrastructure. And land surveyors, what they generally do is they are responsible for performing all of your measurements on a site for a design and construction project. So one of the techniques that land surveyors do very frequently and civil engineers need to be familiar with is called leveling. So leveling is a very general term, and it's applied to determining elevations of points or differences in elevations between points. So when we say elevations, what we're really referring to is like the Z direction or up and down. So elevations being kind of like Z coordinates measured from a level point or a level line called a datum, and looking at those differences in elevations. And this is really important, again, in the construction and civil engineering design fields, okay? Now, one common, and in fact it's the most common type of leveling, is called differential leveling. And this is what this video is really focusing on. So we're going to write this down: differential leveling. Okay, now there are other kinds of leveling procedures as well, but this is the most common one. So differential leveling is basically done in the following process. First, a telescope known as an auto level is used to read graduated rods held at specific points. Now, these points are usually on the ground surface, okay? So picture someone holding a big, long rod that has a graduated lines on the rod, like a giant ruler, okay? Now, basically what happens next is a horizontal line of sight within the scope is established. Okay. Now, again, the instrument we use, the telescoping instrument we use, is often called an auto level. There's another instrument called a total station that can also be used, but often we use a non-electronic auto level. Okay. So the instrument, we'll make a note of this, the instrument, which again is usually an auto level, or I'll put a note here, or total station, is set up on a tripod approximately halfway between a point of known elevation and the new point where the elevation is to be determined. Okay, so the instrument, or the auto level more specifically, but I'm going to keep it in general terms, the instrument is leveled. That means that there's a little leveling bubble on the instrument that we make sure that the level bubble is within a particular target zone. So the instrument is leveled, and a back sight, abbreviated BS, is taken on the rod held at the first or known point. Okay, so basically you have someone looking through the auto level scope, which again is looks like a small telescope, and they're reading a value off of this graduated rod that's being held at the point where you already know the elevation. Okay, now this is the reading on the rod held at the point that we already know. Okay, now we use this reading to determine what's called the height of instrument. Okay, so we're going to say this reading is used to determine the, well, let me color coordinate actually, let's write this in red, to determine the height of instrument, which we abbreviate HI. Okay, so the height of instrument, the HI, is the vertical distance from what's called the datum, and I'm going to use a different color here, from the datum to the line of sight of the instrument. Now, I'm going to draw a nice figure for us in just a second, but right now I'm just giving the explanation and some of the vocabulary words. Okay, so don't worry, we're going to have a nice figure that accompanies this explanation in just a second. So again, in equation form, I can say height of instrument equals elevation A plus the back sight. Now this elevation right here, when I say elevation A, that's the elevation of the known first point. Okay, so that's the point I'm referring to right here. It's a point where you already know the elevation. So that's what we're calling elevation A. All right, now what happens is you then turn the scope around. So we're going to say next, the scope of the auto level is rotated and a reading on the rod held at the new point is taken by what's called a foresight, which we abbreviate that FS, okay? Now, to obtain the elevation of this new point, we do the following. We're going to say to determine the elevation of the new point, we do the following. We say ELEV, and I'm going to call that sub B, referring to the new point, equals the height of the instrument. Now, when we say the height of the instrument, we're saying HI. That's this same HI right here. And then we say minus the foresight. Okay, so again, what we've done is we've used a known elevation of some point A, and we add to it a backsight reading to get the height of the instrument. Then we calculate an elevation of a new point that we're interested in, calling it point B, by taking the height of the instrument we just calculated and saying minus this thing called the foresight. So let me draw a picture of this, because again, I can explain this all day long, but it's a lot easier to understand if I draw a picture. So I'm going to draw a picture of a sloped piece of land. Okay, so this is supposed to be like a piece of land that we're looking at it from the side. And I'm going to say that the point that we know the elevation of is right here. I'm going to call this point A right here. Okay, this little kind of shaded in box. Okay, and then I'm going to say that the point that we're really interested in is up here somewhere. I'm going to call this point B. Okay, now I used this word called datum a few minutes ago in the video. So a datum is simply a reference axis. Okay, so this is our datum right here. And a datum, again, it just means reference axis. And it's an axis of some kind of known elevation, okay? Now, often we just call a datum 0, okay? So you can, in math terms, you can think of a datum as maybe like your x-axis. It just represents 0, so or what you're calling 0. Everything is referenced back to the datum. So I'm going to say that the elevation of the datum is 0.00 feet. Okay, now sometimes we call the first point that we know the elevation of, we call that a benchmark. Okay, so I'm going to make a little note here. I'm going to make a little arrow here. I'm going to say the first known elevation point is sometimes called a benchmark, which we abbreviate BM. So if you ever see the vocabulary word benchmark or you see the abbreviation BM, that just refers to the very first point where you know an elevation, okay? So here's what we do. We take our instrument, which typically is an auto level, and we set it up on a tripod. So I'm going to draw a little tripod symbol here, and here is my instrument. That's my little scope, okay? And we set it up approximately halfway between the point that we know the elevation of and the point where we're trying to determine the elevation, approximately halfway, okay? And then what happens is you have one person standing near the point where you know the elevation of. So I'm going to put the rod here, and I'm going to have a person standing right here holding the rod, okay? So this right here, let me change colors. This right here is our rod. Its full name is Philadelphia rod. Okay, so that's often abbreviated as Philly rod or just rod. Okay, now another person is going to be standing here with the instrument. Okay, and she's going to be looking into the scope. Okay, now when she's looking into the scope, she's going to read a value off of this rod. okay? And that is going to be the backsite value that she reads. So this dimension line right here that she reads, this number she reads here, this is the backsite, okay? And she writes that down in her notebook, all right? And then what happens is the person holding the rod, sometimes called the rod person, is going to pick up this rod and move it to the new point, okay? So we're going to say this person right here is going to pick up the rod and move it over here, all right? So for the sake of clarity on this video, I'm gonna maybe just do some editing and do some erasing here. But basically, again, this person is gonna move the rod over here, all right? So what happens is this person's gonna move the rod and he's gonna be standing right here, all right? And same guy holding the rod there. And our person running the instrument here, she's gonna swivel this around, okay? This is gonna be on like a little rotating pivot here. She's gonna swivel this around and she's gonna stand on the opposite side now, okay? Now when she's standing on the opposite side, guess what she's gonna do? She's gonna take another reading on the rod, but now the rod and the rod person is standing at, didn't mean to erase that, is standing at point B, okay? Now when she reads this measurement here, this is the foresight measurement, okay? That's the foresight measurement. So what she's able to do now, or what they're able to do, this is at minimum a team of 2 people, is they can calculate these things that we already talked about. We can say that, again, the height of the instrument, HI, is the elevation of point A plus the backsite, okay? And remember, the backsite was the number read off of this rod right here, so it's literally this distance. And then when we want to calculate the new elevation of point B over here, we say ELEV of point B is equal to HI minus the foresight. So where are these values here? Well, the first value that we need to make sure we're able to identify is this value right here, okay? The distance from the datum up to where point A is, that's the elevation of point A. That's the known elevation. Again, if it's your first known elevation in the process, you often call it a benchmark, okay? So if you just look at the 2 dimension lines, if you say elevation of point A plus backsite, what do you get? Well, you get this dimension here. That's from the datum to the line of sight of the instrument, and that's the HI, okay? So again, you can draw this geometrically and add and subtract accordingly to figure out what these values are. Then to finally get the elevation of point B, which is this dimension line right here, it's the distance from the datum to point B, we take the height of the instrument and we minus the foresight. So you take this full height of the instrument, HI, and you say minus foresight, minus this little distance here, and guess what you're left with? You're left with ELEV of point B, okay? Now, why is this important? Well, in civil engineering, whenever we're designing systems that are going to be built on a site, one of the things we often have to deal with is what's called earthwork. We have to cut and fill and move around soil on the site. Now, performing differential leveling operations like this gives us the information we need to calculate how much soil we need to cut and fill and move around on a site so we can create the proper leveling on the site for our construction project, whether it be a building or a roadway or something else. So that's just one important example of differential leveling. So hopefully you found this video informative. I'm going to have another video or so where I do a numerical example, but this was just meant to give you some background information and some good conceptual knowledge of differential leveling. If you found this helpful, please hit like and subscribe.